Continuing on with our discussion of tangents, in this video we're going to jump back into our code and begin our implementation. And Lee's also going to do a little setup to demonstrate exactly what he's talking about visually inside of Unity as well.
Right. What I wanted to do also is inside of Unity before we get to the code is set up our project a little bit again before we go in. But I also wanted to show something that I forgot to mention in the last video.
Set up our project before we go in? You lost me.
Yeah, I do that sometimes. This project, before we go into code and start setting some stuff up, I want to set Unity up, make some changes to the config file before we start coding stuff.
Okay, I gotcha.
And just basically get Unity ready to go, because some of the stuff that we're going to be testing is going to be computationally intense, especially once we start drawing the vectors for the tangents.
Okay.
So if we tried to do that with the terrain the size it is, we would probably crash Unity.
I gotcha.
So, but the thing I wanted to show that I forgot to mention in the other video is if you don't calculate tangents on your mesh, your shader will actually tell you if it doesn't find any tangents. That's what this warning's all about, where it says shader wants tangents, but the mesh doesn't have them. So if you see that, that's because you didn't calculate your tangents. So the other part that I want to do, like I said, we had some setup work that we did before, or need to do before we start coding. One is I want to get rid of the normals. So I want to turn those off or get rid of the normal map. So that'll simplify our preview. Let's go back over into code, go to the config, and patch vertex count. We're going to drop this back down to 5.
Okay.
Build out. And go ahead and jump back over here. Play it, make sure it does what it's supposed to do.
Okay, looks good.
Center everything up. So we get our patches like we expect. All right, and go ahead and stop that. Now let's go back into code. Now it's time to implement our tangents. Now, the cool thing is the code that we showed from the one website in the Firefox, inside of Firefox, from the link that JJ Guzzardo, not JJ Abrams, posted, has this fairly intense way about going through and calculating out all of our tangents. We're not going to do this. This is designed, again, more for a model that has vertices that are wrapping around a surface. If you were to think like a character, a humanoid character, where you've got vertices that wrap all the way around an arm and a leg. So the UVs are switching orientations. The vertices are switching orientations. They're flipping upside down, doing all kinds of crazy stuff. Our terrain doesn't do that. We know that it's based off of an equally spaced grid of vertices, so we don't have to worry about that. We also know that, if I get back over into Photoshop, that we're going to align our tangents such that the tangent for every vertex in our mesh is going to be aligned along the z-axis.
Right.
That will also simplify our calculations. It would also mean if we were to calculate out our bitangents, we can assume that those will all be aligned along the x-axis. So one of the things that I'll do real quick is, let's go ahead and hide these. I'm going to create another layer real quick, just because I like layers. They're so fun. Get rid of this purple color. All right. Now, we said that we've already calculated a normal. So let's say we've got some normal that happens to be at 45 degrees. So for some reason, we have a face. I almost got that.
That's good enough. So basically some type of slope right there.
Yep, we've got a slope, and we've got a normal that is facing off of this.
Mm-hmm.
And let's say, for sake of argument, that we know that our z-axis is this way. So this is our z, which means that when we draw our tangent, it needs to be going along the z-axis. But we also know that our tangent needs to be perpendicular to our normal,
Mm-hmm.
which means that it has to look something along the lines of this.
Right.
So we could do all the really complicated math to figure all this out, or we could just do a slope calculation that says, let's take this height and this height. Hold on, let me get a brush. I'm not going to try to draw the two with a line tool. So if we take those two heights, then we take height 2 and subtract height 1 from it,
Mm-hmm.
it gives us our slope. So then we can set the y component of this vector to be our slope. We know that z is going to be 1, or the spacing that we're using for our grid.
Mm-hmm.
So we'll set z to be our spacing. Because this is along the z-axis, our element for our x will be 0. So we can derive our vertex with a single equation as opposed to that big, long, drawn-out process,
Mm-hmm.
just because of the fact of the nature of our grid. So that will simplify our calculations. Now, a tangent, though, in computer programming is saved as a vector 4. It actually has an x, y, z, and a w component. Now, the w component determines the handedness of the vector, whether it's a left-handed or a right-handed vector. In short, what that boils down to is it determines whether or not your bump map, if white is going to be the bumps or black are going to be the bumps, which way the bumps are pointing, up or down. So you could calculate that, or because our terrain is always going to be facing the same direction, we can hard code in the handedness for our tangent. In our case, it's going to be a -1. So your handedness is going to be either a -1 or a +1, depending on if it's left-handed or right-handed.
Okay.
So, and I'll show both, and you can just go, oh yeah, well that one looks better, so you set it to that one. It's not rocket scientist, which is why I'm doing this. All right, so let's get back into code. Now, for the really, really hard part, all that fancy math that we need to do our creative thinking version of tangents. We'll copy and paste our calculate normal, rename it calculate tangent. Everything here is going to be the same, but we're going to be returning a vector 4 because tangents are vector 4s. We need to know what our full spacing is, so we're going to keep that line. We only need to know the difference in height for our up and down samples because we are sampling along the z-axis. If I get back over to Photoshop and turn this one off, turn this one back on, we are sampling on any given vertex the point directly above it and the point directly below it. This will give us our slope for our tangent.
Mm-hmm.
So we're going to need those 2 sample points. So that gives us our up and down. We're going to change out the way we're calculating this. So I said because this is z aligned, our x component is going to be 0. We're going to take our up point, subtract our down sample from it, or sorry, our up sample, subtract our down sample from it. We know that the z contribution is going to be our space. And from testing, I know that I want my tangent to be, I believe, -1, or will be -1, which I believe is right-handed. So, and I'm going to set our type to be T instead of M because this is tangent, not a normal. And I need to normalize my tangent before returning it. Now I have an error here because I haven't changed this to a vector 4. So if I change that to a vector 4, everybody should be happy. We should be able to calculate tangents if we call them. So we need to go ahead and call those. We don't have an array to hold them yet. We need to create one. So we'll come up here, create a new variable called tangents, assign it a new vector 4 array of mesh dot vertex count, because we need exactly one tangent for every vertex in our mesh. Hit semicolon, give it a sec to update. There we go. Now to calculate them, so we're going to say tangents sub I equals our calculate tangent, and we send in our vertex. Return that out. Whoops, semicolon, not L. I almost got that right key. And then we need to assign them. So we say mesh dot tangents equals our tangents. So that will calculate our tangents, but how do we know if they've been calculated or not? We'll go up here. We're going to turn back on our code that draws those nice little lines that represent our vectors. So Control K, Control U to uncomment those. And we're going to go ahead and get the positional information. We need to draw some information based off of our tangents. But before I do that, I want to make sure that we have tangents in our mesh. If we don't have tangents for some reason, this will get very upset at us. So we need to go ahead and check our mesh filter, get its mesh, look for the tangents, check its length, and make sure that it's greater than I. Not a semicolon. Come on, catch up.
Okay.
There we go. All right, so let's go ahead and take care of calculating out a vector for our tangent. So what we'll do is we'll make a new variable called tan to hold our tangent. This will be a new vector 3 because we don't need the handedness for drawing our visual representation of it.
Mm-hmm.
So this will be our mesh filter dot mesh dot tangent, and we'll get the element that we're currently on. We're going to get its x, and I'm going to copy and paste this. So basically, I'm just building a new vector 3, stripping the W component out. So that will take care of that part. Now to draw it. So we go debug dot draw line. We're going to draw this from our, let's see, actually I did save that out. So we'll draw it from our position plus position, because I have to align it to our world position as opposed to local. So that will be our starting point. Our end point is going to be our position plus position. So POS plus position. So where we started from. And we're going to draw all the way to the end of our tangent. So we're going to add the tangent to it.
Mm-hmm.
And then I'm going to give it a color. Because this is going to be along the z-axis, I'm going to give it a color of blue to match the standard z-axis. And because our normal is along the y, I can readjust this to be yellow. Hopefully that'll show up decently. Well, no, we already proved it. Yellow doesn't show up well, so let's keep it for black for now. We'll change it to yellow once we put the texture back on. Something else I was just thinking about.
Mm-hmm.
I'm going to take our plus position here. And I'm going to add it up here just to simplify it. I'm just cleaning it up so I don't have to type it over and over again.
Sure.
Even though I've already done it. So, because it's the same everywhere. All right, so that takes care of that part. If I go ahead and build it, make sure there's no errors. Jump over to Unity. If we run, if everything works well, we should have a black line drawing in the direction of the normal of our surface.
There we go.
And a blue tangent, which we can see blue, and they're all pointing in the direction of the positive z-axis. But the cool thing is, if I start rotating the camera, you can see that our tangent are all aligning with the surface. So if you notice, they're not perpendicular.
Yeah, I was going to ask about that.
The reason why they're not perpendicular is because inside of our code, we're cheating the cheat where we're calculating our normals.
Mm-hmm.
We took our y component, which was supposed to be a full space,
Mm-hmm.
and we divided it by 4 to darken our shadows.
Oh, yeah, that's right.
Which is, we've basically just took all of our normals, which should technically be facing perpendicular to the surface, or so straight out of the surface, and we've kind of forced them to lay away from the light source, or away from the surface, which makes them accentuate the shadows.
Mm-hmm.
It's just a cheat. Something to do calculationally that is inexpensive and gives us, the result we want. Artistic license, if you would. So if I take the division off, and we jump back over here, now we get our perpendicular lines, which is where you're probably about ready to go. It's like when you said perpendicular, they're not.
Yep, it was. All right, very cool.
So now, I had mentioned that there's another vector that is perpendicular to both of these. That's called the bitangent.
Mm-hmm.
Sometimes you will see it in a term called binormal, and they get used interchangeably, but according to that one website in the book, the mathematic books where I've read, binormal is actually something that they use for calculating curves. This is supposed to be a bitangent, not a binormal. So, but I don't have a PhD in mathematics. So if I'm wrong, forgive me, but it'd be help if I was inside of your computer and not mine clicking on stuff. All right, so let's calculate out the bitangent. So if we go back up here where we're drawing out the other line, I'm going to use the dot product or the cross product to figure this one out. So we'll calculate out the bitangent. So that's going to be equal to the vector 3 dot cross product of our normal, which is going to be our mesh filter. So I'm just going to copy this line. So we're getting, let's see.
Copy it one down below that on the debug draw line.
Yeah, it's like going, I know it's got to be there somewhere, and I was going to It's like, do I have to type it again? What? No, we're drawing it somewhere. There we go. So we're copying our normal, and then we're going to cross that with our tangent, which will give us a normal that is perpendicular to the 2. So I need to draw that. And because of the way we've designed the calculations to work, this tangent should be perpendicular to both of those aligned along the x-axis, which is traditionally colored red. So we'll make ours red.
You want to go ahead and change your tan to BIT?
No.
Okay.
I want to be confused why I've got purple lines.
Cool.
So if I go ahead and hit play again. Now cross products are fun. So now I have my bitangent as well as my tangent as well as my normal, and they're all following the surface.
Mm-hmm.
And we've done it with far fewer lines of code than the traditional way of doing it. So it doesn't make mine better than others. It's just in this one case, because we're doing terrain that's based off of a height map that has a very particular shape to it with equally spaced triangles, we can do it in this fashion. Now, something to note is the fact that when we get into large meshes with this particular technique, like we were discussing with the normals, this is slow because we're doing a lot of lookups on the terrain generator, which means it's going through and calculating out the heights at each one of those points using our terrain generation algorithm. So if I jump back into code, every time we are doing one of these calculate normals, we have to do 4 lookups against the terrain generator, and we have to do 2 additional ones for the calculate tangent. So that's 6 lookups at every vertex, not counting the lookups that we're already doing when we're creating the mesh or creating the grid to begin with, because we're also doing lookups there. So when we're creating our mesh, we've got 8 different lookups for each point along our grid. This is expensive, very expensive. One of the things that we're going to get into, one of the future R&D sessions that's going to probably come up right after we finish the sculpting, as we start looking at making our sculpting tools persistent, is going to be implementing a vertex cache. So what we're going to do is make a system that is responsible for generating the information for each one of the terrain patch vertices. So when we need to get the information, we'll go to the vertex cache, ask it for the information. Basically, it'll go, hey, do you have the information for this vertex? If it does, it's going to return it. If not, it's going to go calculate that information, store it in the cache, return that information, and it'll keep it in the cache until that vertex is no longer inside of an area of interest. Basically, once we will set some sort of distance that says once the player is X distance away from this vertex, start counting down a time to live, which will say, okay, the player hasn't been near this vertex in the last 10 seconds. Go ahead and get it out of memory. We're not going to need it anymore. Now, again, the distances and times are going to be something that we just play with. But the reason we need something like a time to live is so we can look at our cache. If a player moves 10 units away, and let's say our distance is 10 units, the moment our player moves, 10.1 meters away, the vertex drops off the cache, and the person goes, oh yeah, I need to turn around and go back. They step back immediately, and then it's got to recalculate that mesh.
Right.
So there's no real point in doing something like that, where if we've got a time to live, we give the player a time to come back before it drops off and has to recalculate. Now, there's a couple of different ways we can look at it. We do a time to live, which would be one way of doing it. I've also seen systems that use 2 different radiuses.
Exactly. Yep.
So they'll have a system where the moment you leave the first radius, it gets flagged as a possibility to be dropped. The moment they leave a second radius, it then gets dropped. So a lot of this still needs to be R&D, and what we end up with as a final solution will be whatever works best. So let's see, I've got that working. Let's go ahead and turn this back to yellow, because I want it to be yellow, because we did all of this work, but we haven't shown yet why we did all this work. So if we go back over here, let's go ahead and put our normal map back in. So if I go ahead, let's save this out. Go ahead and hit play. Give it a sec to calculate. So now,
Big difference.
yeah, we get something that looks like a bump map should look.
Very cool.
So we get to have some fun with that. Notice we also don't get the error that says, the shader expects tangents, and there aren't any.
True.
So now we've got that. Let's go ahead and stop this. Let's put our texture back on it. And then we can build it out again, or play it again. So we can't really see it now, mostly because of how small it is. And if I hit show gizmos, now you can see the yellow and stuff. All right, let's see if we can get the bump maps to show up a little bit better. So let's go with back into code. Let's comment out all of our little gizmo drawing stuff. So that'll take care of that. I want to see how much we're texturing as well. Okay, so that looks right. Let's go ahead and set our patch size back up to 25. And let's go back into Unity. And I wonder what I've got mine set to. Let me check real quick. Nope, I left mine at 1. All right, so that's at that, up there. All right, let's see what happens. I turn off show gizmos too. All right, you can start to see it. Let's see if we can accentuate that even more. So if we go into our height map, we can take our bumpiness, crank it up, hit apply. Now we can see it more.
Yeah. Cool.
And then depending on what you want to do, if we stop here and we go into our UV, let's set our scaling. Let's go with, say, 2 and 2 here. And is there anything? Oh, yeah, there's something else I wanted to show too. Let's turn this off, because this will show up better on white. Because I mentioned that I wanted, let's render it right now with right hand, or it's set to -1 in the handedness.
Okay.
And then I'll flip it over to the positive one so we can see the difference.
Alrighty.
So if you look at it now, it's more like the white is the high and black is recessed. And if we go back over to our terrain patch and we flip this, again. And if it has a different look, it's subtle, but it's different than the other way. So it's just a matter of how you want the lighting on your bump maps to work. Now we're using a copy or an instance of our material with the way we create our terrain patches. So if you go in here and see, will that, oh.
There you go.
So if you adjust things here, it doesn't apply. So if you're wondering why you can't tweak anything, it's because it's a copy, not the same information. So any change that you make here, you have to stop and start again before you see it. The difference is the normal map. You can make changes here, apply them, and they do take effect in real time. So if I were to dial this down, I get less of an effect. And this is a good technique if you're trying to dial in the look of a bump map. It's much easier to set your material to none on the base.
Your texture?
The texture on the base material, or the material's base texture,
right.
to nothing. Render it out as white. Dial in your bump map until you get what you want, then put the texture back in. So I want to bring this up to 3. I'm going to hit apply on this, and let's stop this. Let's go back and switch the handedness again. And I've also promised that I was going to show why I don't like parallax map. So if I go back over here, let's take our height map. I'm going to duplicate it. So Control D to duplicate it. That gives me height map 1. And just take the space out. Let's go ahead and change it. I don't want it to be a normal map. I would just want it to be a regular texture. Go ahead and hit apply. This will turn it back into a grayscale. Now if I go back over to my material, if I switch up to a diffuse or parallax diffuse, I add height map 1 in for my height map, and then we add in our grass texture. There we go. We go ahead and let's crank this up a little bit more so it becomes more obvious. We hit play. Now, it looks a lot like a bump map. What I don't like about it is if you move the camera really close to the ground, as in the camera touching the ground, and then you start moving around the camera, it's kind of hard to see. But if you start moving it around in certain ways, especially when you get up in the hills, you'll see the texture start to crawl along the surface. I don't know if you can get it to do it. I'm picking up lag, so I won't be able to see it.
Right. Not yet.
It's usually when the camera is right up against the surface.
And much as it'll let me, that's up against.
Okay, so you're not seeing it then?
No, it looks great, actually.
Oh, okay. Well, I've seen problems with it.
And that looks pretty awesome up there. I'm just saying.
Yeah. But trust me, I've seen problems with it. I may have screwed something up in a previous test with it.
Oh, nope, there it is. There it is.
Oh, yeah, you see it? All
now
right,
I got it.
yeah. Like I said, it's not all the time, but it does start showing up from place to place.
Gotcha. Wow. Yeah, that looks horrible.
And yeah, and it's bad when it happens.
Whew.
Which is why I don't use it.
Gotcha. Too
Now,
bad, because that looks awesome.
Yeah, it does look good up there. But it doesn't look much different from
if you just...
the bump.
Okay.
Yeah, if we got to stop at the switch. You
Right.
can't switch the shader. It does definitely, at the distance, it does look cooler than bump map. But bump map's pretty close. But it's... So... I was thinking about implementing something similar, but having it as an effect that only happens X distance from the camera.
Gotcha.
So when you get close, there's no parallax to the camera, so it just stays at your distance. But if you turn around and look up in those hills, it's not much different. It's still
not bad.
I mean, all the detail that you're getting based off of that, I mean, you think about it, that's still a fairly low-res mesh,
right?
In a single texture, in a single normal map, and we're getting a lot of believable terrain type detail. So, what we'll probably end up doing is with our shaders experiments, we'll figure out a way of using a texture map that has one texture map that has multiple textures of diffuse maps. And a second texture map that has normal maps. So when we're doing our procedural generation of the terrain, we'll have different types of bump maps depending on the type of terrain.
Gotcha.
So they match up.
Cool.
So we can keep this type of look, but with multiple types of terrain all blended together.
Okay, so well then this pretty much wraps up session 6, right?
Yep, that should be it. Now you can get this implemented and have some cool looking information. We will be turning this off when we start with the sculpting tool because until we get the vertex cache operational, this method is going to be too slow to run with our sculpting.
Okay.
And it also exaggerates the problem with loading textures. And I had pointed out, nobody's taken me up on that challenge yet. Remember way back when we started loading the terrain as you walked around? And I told people that there was a way that they could smooth that out even more by using the same type of delayed loading system as we were using for deleting. Nobody's taken me up on that yet. I've seen lots of forums complaining that it takes too long to load up a row of patches, but nobody's implemented that yet. I guess they just all rather wait for threading. So, but yeah, it's all good. Though somebody did take me up on my challenge for the noise, which was really impressive.
Yeah, that's Tim.
Yeah. So he said he was looking forward to these videos. So Tim, if you see these, good job on getting that implemented. Thanks. It was impressive the numbers you got for speeding up the noise. So I went back and implemented it on mine again just to see what I got, and I've got about the same numbers you got. So Perlin noise is 50% faster than what it was before.
Wow, that's just amazing.
Yeah, good job on getting that in. So yeah, go ahead and implement that smoothing out of the loading of the train and show everybody up on that one too.
All right, awesome. Well, with that is going to wrap up session 6, and with session 7 we're going to be moving over into the start of the sculpting tools. So thank you everyone, and we'll see you over in session 7.